All right, I just want to mention something from the last lecture before we get started. So in the last lecture, we talked about the dual sheaf, and I think there might be an error in the notes, or at least something that's kind of non-standard. And so let me give you the more standard definition. So if we're trying to define F dual, where F is a sheaf of OX modules, what's it going to be on an open set U? Well, it should just be the OX restricted to U module homomorphisms from OX restricted to U into F restricted to U. Okay, the difference between this, I think in the last lecture we defined this a little bit different. We defined this as the hom OXU. If I remember right, this was the definition from the last lecture. But in this case, it's not clear what the restriction map should be, and in fact, I don't think this is the right definition. So let me X that out, and this is the right definition. And this hom here means the sheaf. This means the sheaf homomorphisms. And there is restriction maps here because sheaf homomorphisms by definition come with restriction maps. So I think this is the right definition. Okay, the one thing we need to be careful of here is you need to note that this is an OX view module. All right, so you can think about why that's true. So if you have a sheaf homomorphism, you can multiply it by an element of OX of U, and you can think about why that makes sense. Okay, so if you want to see a little bit more detail, I think I answered a question on Moodle about this, so go ahead and look that up. I think there's one homework exercise that uses the dual sheaf, so really want to look at that. All right, let's move on to quasi-coherent sheaves. So let's start out with the definition. So what we're going to do here is we're going to give a class of OX modules of sheaves that are more closely related to commutative algebra. So let's see how that works. So let's let X be. We'll start out with affine schemes, spec R, and let M be an R module. Okay, we're going to define a sheaf on X, an OX module, and we'll call it M tilde by the following. So M tilde on some open set U is just going to be the set of all sections phi, and phi will be a choice of phi p for every point in U, subject to the following compatibility condition, which should look very familiar. So phi p is in the localization of M at P, right? So P here is a prime ideal of R, right? So it makes sense to localize a module at P. And for all P, there is a neighborhood UP of P, and G, the G is going to be an element of the module, F is going to be an element of the ring, so that for all Q in the neighborhood, we have that VQ is given as a quotient of G and F. Okay, and we also need, of course, that F is not equal to 0 for all Q and UP. Okay, it's easy to see from this definition that the M tilde is a sheaf of OX modules. You can see, if you want to multiply by a section of OX, that you just multiply all the phi's by whatever the section is, and that makes sense because M is an R module, so that's okay. It's easy to see it's a sheaf by this local definition, and in fact, this definition is exactly the same as the definition we gave for the structure sheaf of a scheme if you replace M with R considered as an R module over itself, right? So let me write that down here. So R tilde is just isomorphic to OX. So this is R considered as a R module over itself. And if you take the tilde of that, just get the structure sheaf. That's the same definition here. All right, good. So here's a quick proposition. The stock MP, so M tilde P, this is the stock of the sheaf M tilde, and you can guess what that's going to be isomorphic to. This is isomorphic to MP, where this is just the localization of a module at a prime ideal in commutative algebra. Okay, and part B says that M tilde on a distinguished affine set. You can guess what I'm going to write here. This is just the module M localized at the element F. Okay, of course F is in R. Okay, in particular for part B, you can see that M tilde, the global sections over the whole affine scheme X are just equal to M, but because this is just M localized at 1. Okay, I'm going to skip the proof for this, but it's exactly the same as the proof that we did for the structure sheaf of schemes, which I think we also skipped, but it's very similar to the proof we did for affine scheme, for varieties, I mean. So there we go. Now, it's not true that every OX module is of this form. It's not every module, OX module on affine scheme is of the form M tilde for some M. And there's an example in the notes. It's not too hard, but it's not very important, I don't think. So I'm just going to skip that for now, but you should look it up if you're interested. Let's go on to the next definition. We're going to now generalize this to an arbitrary scheme, not just affine schemes. So it goes like this: a sheaf of modules is quasi-coherent if there is an affine cover UI isomorphic to spec Ri. So each piece of the affine cover is isomorphic to spectrum of some ring, and Ri modules Mi, so that F restricted to UI is isomorphic to Mi tilde. All right, so a quasi-coherent sheaf is one that is given by these M tilde modules locally. Okay, and here's the remark. So if F is quasi-coherent, and U and X is affine and isomorphic to, let's say, spec R, then F restricted to U will be isomorphic to M tilde for some R module. M. All right, so the definition just says there has to exist an open cover so that F was isomorphic to some of these tilde modules on that open cover. This remark is saying, in fact, for any affine open set, F is going to be given by a tilde module. Okay, and one more remark that we won't use too much. So F is called coherent if each of the mi's in the definition is finitely generated. All right, so I think the author in the note says that, that most of the stuff we'll be doing will be true for quasi-coherent modules, so we'll work in that more general setting. But in fact, most of the examples we'll be looking at are finitely generated, so they're actually coherent. All right, so let's look at some examples. So of course, OX, the structure sheaf, is coherent. Because OX restricted to U was just going to be isomorphic to R tilde, right, where U is spec R. All right, so I think we already sort of mentioned that. So in particular, this gives us another example, the OX D, so or let's say OPND, the Serre twisting sheaves. So I think in the lecture where we introduced these, we showed that that locally they're isomorphic to. So I mean, I think this is what we proved. That there was an open cover UI, so these were isomorphic to just the structure sheaf, right? And so these are going to be let's see, that's restricted to UI. All right, so these are locally isomorphic just to the structure sheaf. So they are also coherent or quasi-coherent, and okay, but they're not isomorphic, but they're not globally isomorphic to the structure sheaf. So these are some non-trivial examples of quasi-coherent sheaves. All right, and I kind of told you that these are closely linked to commutative algebra. So this lemma here will give us an idea of how closely linked they are. So there's a bijection. Okay, let's see. In this one, we're gonna have x be an affine scheme. So there's a bijection between morphisms of sheaves m tilde to n tilde, and morphism, and then R module homomorphisms. R module homomorphisms. All right, 1 to 1. All right, so if you have R modules M and N, then the R module homomorphisms correspond exactly to the morphisms of sheaves of these tilde sheaves, and vice versa. Okay, so that's part A. And for part B, so suppose we have a sequence of R modules that's exact. So this is exact if and only if the corresponding sequence of tilde OX modules is exact. Okay, and then part C is going to say that this tilde construction commutes with all the sort of usual operations on modules that you like. So you can have the direct sum of m tilde plus n tilde, and that will be the same as m plus n tilde. And same thing for tensor products. And also for the dual sheaf. Okay. All right, so let me just say a few words about the proofs of these. So for part A, to go in one direction, if you have a morphism f from m tilde to n tilde, then we just look at fx, the map on global sections. But remember that we saw the global sections of a tilde module are just equal to the module m. So, all right, so that's one direction. And then if you want to go the other direction, so suppose I had an R module morphism G from M to N. How do I get a morphism of sheaves? Well, notice that the G induces a map on local rings, MP to NP, right? For each prime ideal P, but MP here is we know is isomorphic to the stock of the tilde sheaf. The same thing here. So we have a induced map here. Okay, but then once you have a map on stocks like this, then you can put that together into a map of sheaves. So you could remember the sections of the sheaves are just defined as stocks, as elements of the stocks together with some compatibility conditions, and so that's how you get the map on sheaves. Okay, let's look at part B briefly. So a map of modules. So if you remember from commutative algebra, it turns out this is exact. If and only if the sequence of localized modules, this is 3 here, is exact for all primes. Okay, but remember this is the same as taking the stocks of the tildes, so we can put tildes all on these, and then this is exact for every, now these are points P, and that's exact if and only if the maps on sheaves are exact. So I think that was an exercise from the last chapter that if a sequence of sheaves was exact if and only if it was exact at every stock. Okay. All right, and then for part C, maybe I won't write anything down, but it's the same sort of idea as what happens on B. All these operations, direct sums, tensor products, and duals, commute with localization. So you can define a morphism that way, and then it will be an isomorphism because it's an isomorphism at every prime. All right, so you do something like that. All right, now one construction from the last chapter that we haven't covered is push forward. So it turns out in general, the push forward of quasi-coherent sheaf is not quasi-coherent. But it is quasi-coherent in most nice situations. So we'll just cover one of those situations here. So here's a lemma. So let's let I from y to x be an inclusion of a closed subscheme. Inclusion of closed subscheme. All right. So then, if f is quasi-coherent, let me just write COH from now on. On y, then the push forward is going to be quasi-coherent on x. Okay, and then there's also an exact sequence that goes along with this. So you have this is script I, so it's called the ideal of y and x, mapping to the structure sheaf, mapping to the push forward. Okay, so this sequence, so I get the statement to be is there is an exact sequence. On x, where this map here is the pullback, so this here is the pullback. Okay, and this thing here is called the ideal sheaf. So ideal sheaf of y and x. Okay, that's a little crowded. Okay, but so here's the pullback map, which remember is just basically going to be like restriction of regular functions, and then the kernel of the pullback map will be called the ideal sheaf of y and x, and it will be an OX module. All right, so for the proof of part A, so let's recall that for a closed subscheme. So, well, okay, let's first restrict the affine case. So let's just do the affine case. You know, everything is going on. Part A is local, right? Being quasi-coherent is a local condition. So we can just do the affine case. So y is a subset of x, a closed subscheme. That means that the x is equal to spec r for some ring, and y is equal to spec r mod I for some ideal. And furthermore, the pullback map here is going to be something like it's going to be r mapping to r mod I. Okay, and this is a surjective map. Okay, and the kernel is just going to be the ideal I. So this is a exact sequence of R modules, right? And if you just take the tildes of all these, right? Then this will be exactly the thing you want from part B. So this here will be the ideal of y and x. This will R tilde is just OX, and R mod I tilde is the push forward of OY. All right, so I guess that's kind of the proof of part B rather. So maybe I should change that. All right, and then in the case of part A, so because f is quasi-coherent, that means that f has to be equal to m tilde for some R module, if still in the affine case. Sorry, not an R module, because this is quasi-coherent on Y, so it has to be an R1 R mod I module. All right, so then the push forward onto X, so will just be equal to m tilde for the same m, but now considered as an R module, right? Because you have R mapping to R mod I, so through this map you can get an R action on M. Okay, so that's basically how that works. Okay, so there's maybe a few details to worry about, but I think those are the important ideas. When you push forward a module, you're just extending the scalars like this, and the ideal sheaf is affine locally just the ideal. So remember, ideals are R modules, right? They're submodules of R. So yes, good. Let's return to the example we did last time with the skyscraper sheaf. So let's recall the setup there. So we had P was equal to the point in homogeneous coordinates 1, 0 in X, which is P1 in this example, and I was just the inclusion map from P into X. Okay, and then we had our standard open cover, and we also saw that the push forward of OP was just the skyscraper sheaf KP. Skyscraper. Okay, and I think in that example we had an exact sequence that looked like this, where OX mapped to the push forward of OP, and we saw that the kernel was isomorphic to OP1 of -1. All right, so that was from last time. Okay, so what can we see from this right away? We can see that this thing here must be the ideal sheaf. So because this map here is the pullback map right here, or the restriction map. So this kernel must be isomorphic to the ideal sheaf. So the ideal of P, the point P in P1, is isomorphic to OP1 of -1. Okay, and the other thing I want to notice is let's remember what this map here was last time. So I think this map was x1, where the coordinates here are x0 and x1. Right, so basically it's saying the functions that vanish at this point are exactly the functions that are multiples of x1. That's basically how to think of that sequence. But this also helps us see what's going on with this. So I lower star OP is quasi-coherent, and let's see that explicitly. So on U0, this is the place where the x0 coordinate is non-zero. So this is isomorphic to spec kx1, right? Then what does the sequence look like? The sequence really looks like you just have the ideal x1 being included into kx1, and then mapping into. All right, so I'm claiming on U0, if you take this sequence up here and restrict it to U0, then it's exactly this. You just have the ideal including into the structure sheaf, and then you have the quotient right here. Okay, and then of course on U1, then this just becomes this. There's the point P, the skyscraper sheaf. The point P is not included in U1, so the sheaf is just 0 here. So you just have this sort of trivial exact sequence. Okay, good. So that this is sort of the nice way to think about the skyscraper sequence and these sequences of ideal, or sorry, the ideal sheaf corresponding to closed subschemes. Okay, so let me just end by this remark that closed subschemes of a scheme correspond. So this is a one-to-one correspondence with subsheaves of OX. Okay, and so these subsheaves of OX are called ideal sheaves. Why? Because a submodule of R, considered as an R module, is exactly an ideal, right? And so a subsheaf of OX. This is what do I even mean by that? I mean for every U, then I of U should be a sub OXU module of OXU. So that's exactly an ideal. Okay, and so these are called ideal sheaves, and they are one-to-one correspondence with closed subschemes. So you can think about how that works. So for example, you pick an affine open cover. So then this becomes like Ri tilde, and then this will be some ideal here, and this will map to R mod I. And then you have these spec R mod I's, and these here will be exactly the things that are defining your closed subscheme, and you can work it back the other way too. Okay, so think about how that works. All right, so I think that's all I'm going to say for today, and we'll finish up quasi-coherent sheaves next time.